Welcome to a lesson with Dr. Powell. Let's take a look at the last video where we were rotating a conic section by looking at a symmetric matrix here, a bilinear form, if you will. Uh, in order to describe this equation, this left side of the equation, we can think of it as a matrix product right here. This 4 and 4 were right there. Take a half of 10, so 5 and 5. And we're thinking about this like this. So this equation right here would be equal to, set equal to 9. That's another way of rewriting that right there. Okay, now in the process of what we did, we diagonalized this matrix, so rewrote it like, so we know that if we take this and we rewrite it this way, we end up getting a diagonal matrix like this. Okay, what's the effect on this graph? Let's think about that a little bit more. Okay, let's think about the left side as being a function of x and y, and it's equal to 9. Think about what's happening on the function side. Okay, so right here. Normally the input xy goes right here and here. I mean, such as, xy and xy, like that. That's the input. That's where it's coming into the function. Now what we're doing to the input is we are rotating input by pi force, since this matrix right here represents rotation by pi force, by a positive pi force counterclockwise. So we rotate it pi force, the input, and that's what we're doing here. So the effect of the graph is we go pi force a go over here, and that's going to be taken to this function equal to 9, meaning that the solutions are pi fourths a go. So if you go clockwise pi fourths from what the graph is. Currently, the graph f of xy is equal to 9, where f of xy is just simply this part right here. So this graph looks like that, tilted. So if we go, so basically what we do when we input this in is we're taking this and we're taking it back pi force. So this graph goes backwards pi force. The effect is to have a graph like this. Now this graph is in kind of in a more standardized position between the axes. But if you take this new graph and you rotate it pi force itself, counterclockwise, you actually get back to this graph. So that's interesting because this right here, if we wanted to, so this graph right here, we're actually rotating the original graph by negative pi force. But from the new to the original, it's pi fourths. So what that tells us actually is that this rotation matrix that we get in the diagonalization process, the eigenvectors or the columns, actually represent the rotation from the new to the old. So they actually give us the axes. These are the actual axes of the where the original graph was drawn. So the original graph is actually drawn on axes represented by these column vectors. That's one thing to note. Another thing to note is that since this beginning matrix is symmetric, the matrix we diagonalize by, the eigenspaces are orthogonal to each other, which enables us to orthogonally diagonalize this. And by dividing by the length of each column vector, we make this orthogonal matrix, one with an orthonormal basis, meaning that if we take its transpose, we get its inverse, which makes it really nice in this case. So in particular, that allows us to think about this, where this rotation matrix, just taking the transpose of it, so transpose, that's actually the inverse. So that's exactly what we wanted right there. Okay, with just those few notes, I just wanted to go over those from the last video. Thanks for watching.